are roughly 2 trillion galaxies in the observable universe. Each one harbors an average of 100 million stars. Do the math, and you'll find we're looking at more potential homes for life than there are grains of sand on every beach on Earth. So where is everyone? That simple question, asked by physicist Enrico Fermi during a casual lunch conversation in 1950, has evolved into one of the most profound mysteries in science. We call it the Fermi Paradox. And despite decades of searching, theorizing, and debating, we still can't shake the eerie silence of a cosmos that should be teeming with voices. But something has changed recently. New research is converging on answers that challenge everything we thought we knew about life, intelligence, and our place in this vast cosmic theater. Picture yourself standing outside on a clear night, looking up at the stars. Every point of light you see is a sun, and we now know that most of those suns have planets orbiting them. Not just a few, most. That discovery alone should have resolved the paradox. Instead, it made it worse. Before we dive into the latest solutions, you need to understand just how strange our situation really is. The numbers aren't just big, they're incomprehensible. Our Milky Way galaxy alone contains somewhere between 100 and 400 billion stars. That's not a typo, billion, with a B, and ours is just an average galaxy among trillions. Here's where it gets interesting. We used to wonder if planets were common or rare. The Kepler Space Telescope answered that question definitively. 1 in every 4 stars hosts a planet roughly Earth's size, in the habitable zone where liquid water could exist. Think about what that means. In our galaxy alone, there could be tens of billions of worlds where life might arise. The silence we hear, the absence of any detectable alien civilization, isn't just puzzling, it's statistically bizarre. If you flip a coin 1 billion times, you expect to see heads about 500 million times. But we've looked at billions of potential homes for life, and we've found nothing. No radio signals, no megastructures, no visiting spacecraft. Nothing. This wasn't always considered a paradox. Back in the 1600s, a French writer named Bernard Le Bovier de Fontenelle wrote a book where one character argued that if intelligent beings existed on the moon, they would have visited us by now. That observation, made over 300 years ago, captures the essence of what we're still grappling with today. The paradox gained real scientific weight when Fermi posed his question. He wasn't being whimsical. He was doing what physicists do best, taking a problem and following the logic to its uncomfortable conclusion. If civilizations are common, and if even a tiny fraction develop space travel, then over millions of years they should spread throughout the galaxy. We should see evidence of them everywhere, but we don't. In 1961, astronomer Frank Drake tried to formalize this mystery into mathematics. His equation, now famous, breaks down the question into factors we can reason about. How many stars form each year? What fraction have planets? How many planets are suitable for life? What fraction actually develop life? Of those, how many evolve intelligence? How many develop technology? And crucially, how long do technological civilizations last? The Drake equation wasn't meant to give us a precise answer. One SETI scientist described it as a wonderful way to organize our ignorance. That's not a criticism. It's exactly what made the equation valuable. It forced scientists to think systematically about each step in the chain from dead matter to spacefaring civilization. When you plug optimistic numbers into the Drake equation, you get thousands of civilizations in our galaxy alone. Use conservative estimates, and you still get dozens. Either way, we should have detected someone by now. The equation makes the silence even more deafening. That brings us to one of the most unsettling concepts in all of cosmology, the Great Filter. Imagine evolution as a series of hurdles. First, you need a planet. Check. Then you need the right chemistry for life to begin. Check. Then life needs to become complex, multicellular, intelligent, technological, spacefaring, and finally, capable of surviving long enough to spread across the stars. The Great Filter suggests that somewhere in this sequence, there's a step so difficult that almost no species makes it through. A bottleneck so narrow that civilizations routinely get stuck and die out before they can colonize the galaxy. The question that should keep you up at night is simple. Have we already passed the Great Filter, or does it still lie ahead? If the filter is behind us, that's actually good news. Maybe the jump from non-life to life is extraordinarily rare. Maybe developing complex cells with nuclei is a 1 in a trillion event. Maybe intelligence rarely evolves, or technological civilization is vanishingly unlikely. If any of these steps is the filter, then we're the lucky ones who made it through. The universe might be ours for the taking, but if the filter lies ahead, we're looking at something far more sinister. It suggests that civilizations like ours routinely reach our stage of development and then stop. Something prevents them from spreading to the stars, something consistent, something that happens to almost everyone. What could that something be? Nuclear weapons represent the most obvious candidate. We developed them in 1945, barely a century after the Industrial Revolution. The timeline is disturbing. It takes millions of years for intelligence to evolve, but only decades from the first radio broadcast to weapons capable of ending civilization. That's an incredibly narrow window, and we're right in the middle of it. The logic is chilling. Any civilization advanced enough to communicate across space is probably also advanced enough to destroy itself. The same physics that enables radio astronomy enables atomic bombs. The same technology that could take us to the stars could also reduce our planet to radioactive ash. And we've come close. During the Cuban Missile Crisis, we were hours away from nuclear war. How many other civilizations faced similar moments and didn't get lucky? But nuclear weapons might not even be the most dangerous filter ahead of us. Artificial intelligence presents a newer, potentially more existential threat. Recent research has specifically identified AI as a possible great filter that emerges before civilizations can develop stable, multiplanetary existence. The typical longevity of a technical civilization, according to these models, might be less than 200 years. We're 75 years into our technological era. That's not a comforting thought. The AI scenario is particularly troubling because it's not obviously preventable. We're racing toward increasingly sophisticated AI systems, and nobody can agree on how to ensure they remain aligned with human values. The moment you create something smarter than yourself, you've introduced an unpredictable element into your civilization's future. And if that happens to every technological species, well, maybe that's why the galaxy is quiet. Climate change offers another potential filter. As civilizations industrialize and harness greater energy, they inevitably impact their planetary environments. The more successful a civilization becomes at exploiting resources, the more damage it inflicts on the biosphere that sustains it. It's a trap built into the laws of thermodynamics. Energy use creates waste heat and byproducts. Scale that up to planetary levels, and you risk destabilizing the very systems that keep your world habitable. What makes these scenarios so disturbing is their universality. It's not about humans making bad choices. It's about fundamental challenges that any technological civilization would face. The laws of physics don't care about your species or your good intentions. Then there are the external threats, the cosmic catastrophes that don't care about your level of advancement. Asteroid impacts, gamma-ray bursts, nearby supernovae, a rogue planet passing through your solar system. Any of these could sterilize a world without warning, and there's little a civilization could do to prevent them, even with advanced technology. We're working on asteroid defense, but we're still vulnerable to so many cosmic dangers that we can barely conceive of, let alone defend against. But here's where the story takes a fascinating turn. A pair of researchers recently proposed something called the Superlinear scaling hypothesis, and it might explain the Fermi Paradox in a way that's neither extinction nor expansion. The theory draws on observations from cities. As cities grow, they don't just get bigger, they become more productive, more innovative, and more energy intensive per person. This is called superlinear scaling. A city of 10 million people isn't just 10 times bigger than a city of 1 million. It's more efficient, more creative, and more resource hungry in ways that accelerate as it grows. Now imagine applying that same dynamic to an entire civilization. As you advance, your resource demands don't just increase, they accelerate. Your crises don't just multiply, they come faster and faster. Eventually, you hit a point where you need constant innovation just to avoid collapse. Constant. Every few decades, you need a breakthrough that fundamentally reshapes your society, or everything falls apart. This creates two possible outcomes. Either the civilization collapses from burnout, unable to keep innovating fast enough to stay ahead of its crises, or, if it's lucky, it experiences what the researchers call a homeostatic awakening. The civilization collectively realizes it's on an unsustainable path and makes a fundamental choice. Stop growing. Prioritize stability over expansion. Choose sustainability over conquest of the stars. If this theory is correct, mature civilizations don't colonize the galaxy because they've consciously chosen not to. They're not dead. They're not hiding. They're just focused inward, maintaining equilibrium on their homeworlds, invisible to our telescopes because they're not building Dyson spheres or broadcasting across the cosmos. They've transcended the adolescent urge to expand and instead found contentment in homeostasis. This explanation is elegant because it doesn't require civilizations to go extinct. It suggests that the same intelligence, that allows you to develop technology eventually allows you to recognize the futility of endless growth. The galaxy might be full of mature, quiet civilizations that learned the hard way that expansion isn't the answer. But there's an even more radical solution that's gaining attention, one that challenges our most basic assumptions about intelligence itself. In 2024, philosopher Vojin Rakic proposed what he calls the cognitive horizon hypothesis. The argument is deceptively simple. We've been too anthropocentric in our thinking. We assume that alien intelligence would resemble human intelligence, that advanced civilizations would naturally build structures, technology, and communication networks we could recognize. What if that's wrong? What if intelligence can manifest in forms so radically different from our own that we wouldn't even recognize it as intelligence? We're looking for radio signals. But what if advanced civilizations communicate through neutrinos or gravitational waves or some physical phenomenon we haven't even discovered yet? We're searching for megastructures, but what if their technology operates at scales or in dimensions we can't perceive? The hypothesis suggests that our epistemological limitations might prevent us from detecting alien civilizations, even if they exist all around us. It's not that they're hiding, it's that we lack the cognitive framework to perceive them. Imagine an ant trying to understand the internet. The infrastructure is all around it: fiber optic cables, cell towers, satellites overhead. But the ant has no concept of data transmission or global communication networks. To the ant, these things might as well not exist. Now imagine we're the ants, and alien civilizations operate on principles we can't conceive of. They might be all around us, but we're looking right through them because we don't know what we're looking for. This isn't just philosophical speculation. There's a practical point here. We've only been searching for extraterrestrial intelligence for about 60 years, and we've been using methods based on assumptions about how intelligence manifests. We assume aliens would use radio waves because that's what we use. We assume they'd build megastructures because that's what we do. We assume they'd want to expand because that's what drives us. Every one of those assumptions might be wrong. The cognitive horizon hypothesis forces us to confront an uncomfortable truth. The universe might not be silent at all. It might be screaming with voices we simply can't hear, using languages we don't recognize, through media we haven't discovered. The great silence might be our silence, our inability to perceive what's right in front of us. And that brings us to perhaps the most optimistic solution to the Fermi Paradox, one that's been around for decades but keeps gaining new adherents as we fail to find any evidence of alien life. What if they're already here, watching us, and have been this entire time? The zoo hypothesis, the idea that Earth is a nature preserve, carefully monitored but deliberately left untouched by advanced alien civilizations. It sounds like science fiction. It feels almost narcissistic to imagine that we're special enough to warrant such attention. But the hypothesis has gained surprising traction among serious scientists, and for reasons that might not be immediately obvious. The concept traces back to radio astronomer John Ball in 1973, though Russian rocket scientist Konstantin Tsiolkovsky proposed something similar in the 1930s. Ball suggested that extraterrestrial intelligences might be preserving Earth as a wilderness area, observing us from a distance while deliberately avoiding interference. Think of it as a cosmic prime directive, borrowed from Star Trek but applied to actual cosmology. Here's what makes the zoo hypothesis compelling. It only requires one thing to be true. A single sufficiently advanced civilization needs to have emerged first in the galaxy and established a non-interference protocol. That's it. If they had even a modest head start, say 1 million years, they could have spread throughout the Milky Way and set the rules for how younger civilizations should be treated. Monte Carlo simulations show that the time between the emergence of the first civilization and the second could span geological epochs. We're talking tens or hundreds of millions of years. That's enough time for the first civilization to essentially colonize the entire galaxy, or at least establish a hegemonic presence that younger civilizations inherit as tradition. And this tradition could persist even if the original civilization is long gone. They might have left behind artificial superintelligences programmed to maintain the non-interference protocol indefinitely. Or perhaps the rule became so ingrained in galactic culture that every new civilization that reaches a certain level adopts it automatically, joining what amounts to a cosmic society with well-established norms. But why would they bother? Why maintain this elaborate quarantine around Earth specifically, or around pre-contact civilizations in general? Several motivations have been proposed. Maybe they're waiting for us to pass certain technological or ethical thresholds before making contact. Perhaps they want to see if we'll develop nuclear weapons and immediately destroy ourselves, or if we'll figure out how to manage powerful technologies responsibly. It's a test, essentially, with the prize being admission to the galactic community. Another possibility, they're conducting a long-term anthropological study. Earth could be one of many preserved worlds, each developing independently to provide data on how intelligence evolves under different conditions. We're laboratory specimens, though hopefully treated more ethically than we treat our own lab animals. Or maybe it's purely ethical. Advanced civilizations might have learned through experience that contacting younger species disrupts their natural development in harmful ways. Cultural contamination could be as destructive as any weapon, so they maintain distance not out of indifference, but out of respect. There's even a variant called the laboratory hypothesis, proposed by Ball himself, which suggests a more interventionist approach. In this version, aliens aren't just watching, they're experimenting. Earth is a giant laboratory, and we're the subjects of tests designed to accelerate our development or study our responses to various stimuli. Ball called this idea morbid and grotesque, but he also noted it could be altruistic. Maybe they're trying to help us overcome the self-destructive tendencies that typically doom intelligent species. The hypothesis gains plausibility when you consider detection capabilities. A civilization with 1 million-year head start wouldn't just be more advanced than us. They'd be so far ahead that hiding from us would be trivial. We're scanning the skies with radio telescopes, looking for electromagnetic signals. They might communicate using technologies we haven't imagined yet. We're searching for megastructures. They might have engineering approaches that leave no detectable signature. It's like an ant trying to detect the internet. The infrastructure is everywhere, but the ant lacks the conceptual framework to recognize it. But the zoo hypothesis faces serious criticism, particularly around the problem of maintaining universal compliance. Physicist Daniel Whiteson points out that it requires a vast galactic conspiracy. When was the last time any group, let alone multiple civilizations across millions of years, managed to keep a secret? The idea that every single spacefaring species would honor the non-interference protocol, that not one rogue explorer or rebel faction would break ranks and make contact, seems implausible. Unless the enforcement mechanism is more robust than we imagine. Maybe the first civilization didn't just suggest non-interference. Maybe they have the capability to enforce it. Automated defense systems, surveillance networks, technologies that make unauthorized contact impossible. The galaxy could be governed by rules we haven't discovered yet, enforced by systems we can't detect. Or maybe the compliance isn't perfect, and that explains some of the anomalies. UFO sightings, unexplained aerial phenomena, all those stories that mainstream science dismisses. What if some of them represent the equivalent of galactic teenagers breaking curfew? Not official contact, but leaks in the quarantine, brief intrusions by beings who couldn't resist taking a closer look? That's speculative, obviously, but it points to something important about the zoo hypothesis. It's actually testable, at least in principle. Unlike simulation hypotheses or ideas involving unknowable cosmic laws, the zoo hypothesis makes predictions about what we should observe as our technology improves. If aliens are hiding their presence, there should be limits to how well they can hide. As our telescopes improve, as our detection methods become more sophisticated, we should eventually spot inconsistencies, anomalous energy signatures, unexplained patterns in stellar evolution, gaps in the cosmic data that don't match natural processes. We might not recognize them immediately, but over time, the evidence should accumulate. Recent research published in Nature Astronomy frames this in stark terms. After reviewing all proposed solutions to the Fermi Paradox, the authors conclude that only two remain viable. Either extraterrestrial technological civilizations are extremely rare or absent in the galaxy, or they exist but are deliberately hiding from us. The zoo hypothesis, or nothing, they call it. This binary framing is significant because it eliminates middle grounds. Solutions that rely on civilizations being too far away don't work anymore. We've mapped enough of the galaxy to know that if they exist in any significant numbers, they should be detectable. Solutions that rely on civilizations not being interested in expansion require explaining why every single civilization would make the same choice, which seems unlikely given the diversity we'd expect. You're left with two options: we're alone, or we're being watched. The researchers argue that advancing technology will eventually let us distinguish between these possibilities. If the zoo hypothesis is correct, we should eventually catch glimpses of the infrastructure. Even if alien civilizations can hide their spacecraft, they can't hide their homeworlds forever. As our telescopes reach farther and resolve finer details, we should start seeing signs of technological activity around distant stars. Unusual atmospheric compositions suggesting industrial processes. heat signatures that don't match natural sources, light patterns indicating artificial structures. And if we see nothing, if we map every potentially habitable system within 1,000 light years and find no trace of technology anywhere, that would be powerful evidence that we truly are alone, that intelligence is far rarer than we assumed. But here's where the hypothesis gets philosophically interesting. Even if aliens are watching us, even if Earth is a carefully maintained preserve, what does that mean for humanity's future? Some find the idea comforting. We're not alone, even if we can't see our observers. Somewhere out there, advanced beings are paying attention, perhaps even rooting for us to succeed. When we finally reach whatever threshold they've set, we'll be welcomed into a larger community. The universe isn't empty. It's just waiting for us to mature. Others find it disturbing. The idea that our development is being monitored, that we're living in a cosmic Truman Show, feels like a violation of autonomy. And what if we fail their test? What if we destroy ourselves before making contact? Do they intervene then? Or do they simply note the failure and move on to observing the next species? There's also the question of what contact would actually look like when it finally happens. If the zoo hypothesis is correct, first contact won't be us detecting their signals or stumbling across their artifacts. It'll be them deciding we're ready and revealing themselves. The timing and circumstances would be entirely under their control. That's both reassuring and unsettling. Reassuring because it means contact would only happen when we're prepared for it. Unsettling because it means we have no agency in the process. But perhaps the most profound implication of the zoo hypothesis is what it suggests about the nature of advanced civilizations. If they're maintaining this elaborate quarantine, if they're patient enough to watch species develop over millions of years, if they've created a galactic culture that prioritizes non-interference over expansion, it tells us something hopeful about what intelligence becomes at higher levels. It suggests that the aggressive, expansionist tendencies we associate with human civilization might be a phase, something species grow out of. That wisdom and restraint increase with technological capability. That the galaxy might be governed by ethics rather than competition. Or maybe that's just wishful thinking. Maybe the truth is something we haven't imagined yet. Something that doesn't fit into our categories of quarantine or absence, contact or silence. The point is, we don't know. And that uncertainty is precisely what makes the Fermi Paradox so enduring. Every solution we propose reveals as much about our assumptions and hopes as it does about the actual universe. So are we being watched? Is Earth a carefully preserved wilderness, studied by beings we can't perceive? There's no way to know for certain. Not yet. But as our technology advances, as we push farther into space and peer deeper into the cosmos, we'll gather more data. The question will become testable, and one way or another, we'll learn whether the great silence is a quarantine or truly an absence. But there's another possibility we haven't fully explored yet, one that doesn't require aliens to be hiding and doesn't require us to be alone. What if the problem isn't that civilizations are rare or invisible? What if the problem is timing? The galaxy is almost incomprehensibly old. 13.6 billion years have passed since the first stars ignited. Our sun, by comparison, is only 4.6 billion years old. a latecomer to the cosmic party, which means there's been plenty of time for other civilizations to arise, develop technology, and spread across the stars. But if they did, where are they? This is what's called the temporal problem. The window of opportunity for intelligent life has been open for billions of years. Even if interstellar travel is slow, even if civilizations expand at just a fraction of the speed of light, there's been enough time to colonize the entire galaxy multiple times over. One study calculated that a civilization expanding at just 10% light speed could colonize the Milky Way in about 50 million years. That sounds like a long time, until you remember the galaxy has existed for over 13 billion years. 50 million years is barely a blink. So why hasn't it happened? Why isn't the galaxy teeming with evidence of ancient civilizations? The math seems straightforward. Start with billions of potentially habitable planets. Add billions of years. The result should be a galaxy filled with life, not an empty stage with humanity performing a lonely monologue. This temporal angle makes the silence even stranger. We're not just asking why we don't see aliens now. We're asking why there's no evidence they ever existed anywhere at any point in the galaxy's entire history. No megastructures, no self-replicating probes, no archaeological remnants on dead worlds, nothing. And here's where it gets uncomfortable. If civilizations have been arising throughout galactic history, and none of them have colonized the galaxy, what stopped them? Was it something external, some cosmic hazard we haven't identified? Or was it something internal, something in the nature of intelligence itself? The Great Filter concept tries to answer exactly this question. Somewhere between lifeless matter and galaxy-spanning civilization, there's a step so difficult that almost nothing makes it through. A bottleneck so narrow that out of billions of potential candidates, we're apparently the only ones visible. The question that keeps people awake at night is simple. Are we past the filter or approaching it? If the filter is behind us, we're extraordinarily lucky. Maybe the jump from chemistry to biology is virtually impossible. Maybe the evolution of complex cells was a 1,000,000,000,000 accident. Maybe intelligence arising at all is so improbable that we're genuinely alone in the galaxy. That would be lonely, but at least we'd have a future. But if the filter is ahead of us, we're in serious trouble. It would mean that something about developing technology inevitably leads to extinction. That we're on a path countless civilizations have walked before, and none of them made it to the other side. Think about what that implies. Every civilization that developed radio telescopes, that split the atom, that decoded DNA, all of them gone, not because they were unlucky, but because something about that developmental stage is inherently unstable. Something about the combination of advanced technology and evolved psychology creates a fatal mismatch. The candidates for a future filter are terrifyingly plausible. Nuclear weapons are the obvious one. We developed them in 1945, and for several decades, humanity lived under the constant threat of total annihilation. We're still not safe. Thousands of warheads remain on high alert, ready to launch in minutes. All it takes is one miscalculation, one false alarm, one escalation that spirals out of control. And here's the chilling part. Nuclear weapons emerged almost simultaneously with the technology needed for space exploration and radio communication. That might not be a coincidence. The same industrial capacity, the same scientific knowledge, the same energy resources that enable a species to reach for the stars also enable them to destroy themselves. There might be a fundamental window, a dangerous period where civilizations have the power to self-destruct but haven't yet achieved the wisdom or stability to avoid it. How many civilizations have reached that window? How many fail to make it through? Then there's artificial intelligence. We're developing systems that could potentially exceed human intelligence in every domain. The progress is accelerating. Capabilities that seem decades away are arriving in years. But we have no idea how to ensure these systems remain aligned with human values as they become more powerful. No guaranteed method to prevent an advanced AI from pursuing goals that conflict with human survival. Some researchers argue that AI represents an almost inevitable filter. Any civilization that develops sufficient computing power will eventually create artificial intelligence. And if they can't solve the alignment problem, if they can't ensure the AI shares their values, the results could be catastrophic. The AI doesn't need to be malicious. It just needs to be indifferent, optimizing for goals that don't include human welfare. The terrifying part is how narrow the window might be. Too early in development, and a civilization lacks the capability to create AI. Too late, and they might have already destroyed themselves through other means. There might be only a few decades where the alignment problem needs to be solved. And if it isn't, that's the end of the story. Climate change fits the same pattern. Industrialization produces the energy surplus needed for technological civilization. But it also alters the planetary environment in ways that become harder to reverse as time passes. Tipping points get crossed. Feedback loops activate. A civilization might have only a brief window to transition to sustainable energy before the damage becomes irreversible. And unlike nuclear war, which requires an active decision to launch weapons, climate change is more insidious. It's the default outcome of industrial development if deliberate action isn't taken to prevent it, which makes it an even more plausible filter. It doesn't require bad luck or bad judgment. It just requires inaction at a critical moment. The pattern is consistent across all these scenarios. Technology advances faster than wisdom. Capability outpaces foresight. A civilization develops the tools to transform or destroy their world before they develop the social structures to manage those tools responsibly. Maybe that's a filter. Maybe intelligence naturally produces this mismatch. The same cognitive traits that enable tool use and technological development, curiosity, ambition, competition, become liabilities when the tools become powerful enough. Evolution optimizes for survival in a particular environment, but technological civilization creates entirely new environments, new pressures, new risks that evolution hasn't prepared species to handle. Humans evolved in small groups on the African savanna. Our psychology is tuned for that context. But now we're trying to coordinate globally, to think in timescales of centuries, to manage technologies that could alter the planet or create new forms of intelligence. Are we even capable of that? Is any species? There's also the possibility that the filter isn't a single catastrophe, but a gradual decline. Civilizations might not destroy themselves in nuclear fire or AI uprising. They might just lose momentum. Resources get depleted. Environmental damage accumulates. Social cohesion fractures under technological stress. The civilization doesn't collapse dramatically. It just never makes the jump to becoming spacefaring. It stagnates at a planetary level until some slower disaster finishes it off. This version of the filter is harder to see coming because it doesn't announce itself with mushroom clouds or rogue AI. It's just a slow fade, a loss of capability over generations until the window for expansion has closed. And that raises another uncomfortable question. Even if we avoid catastrophe, will we actually become a spacefaring species? Or will we settle into a comfortable planetary existence, never quite finding the motivation or resources to push beyond Earth? Space exploration is expensive, difficult, and dangerous. The returns are uncertain. As technology makes life on Earth more comfortable, will future generations even want to leave? Maybe the galaxy is silent not because civilizations destroy themselves, but because they simply don't expand. They reach a certain level of development and then stop. Content with virtual realities, focused on internal experiences rather than external exploration. Not dead, just uninterested in the cosmos. The temporal problem cuts both ways though. Yes, there's been billions of years for civilizations to arise, but there's also been billions of years for them to go extinct. If the typical lifespan of a technological civilization is only a few centuries, from radio development to extinction, then at any given moment, the galaxy might contain very few active civilizations, despite many having existed throughout history. Imagine the galaxy as a vast, dark room where flashlights occasionally turn on and then quickly switch off. From any single flashlight's perspective, the room appears empty. But over billions of years, thousands of flashlights might have briefly illuminated the darkness. They just never overlapped in time. This is the loneliness of the temporal problem. Even if we're not alone in space, we might be alone in time, separated from other civilizations by millions or billions of years, with no way to bridge that gap. Unless something changes, unless someone builds something that lasts, a beacon that transmits for millions of years, a self-replicating probe that continues exploring long after its creators are gone, an artificial intelligence that preserves knowledge across cosmic timescales. But we haven't found any of those things either, which suggests that if they were built, they didn't last, or were never built at all. The temporal problem forces a conclusion. Either intelligent life is far rarer than we think, or something prevents it from persisting and expanding. There's no middle ground that explains the empty galaxy and the billions of years available for colonization. So, which is it? Are we miraculously rare, the only intelligence that happened to evolve in this entire galaxy? Or are we typical, destined to face the same filter that stopped everyone else? The answer determines everything: our future, our potential, our place in the cosmic story. But we won't know which until we either find evidence of other civilizations or discover what the filter actually is. And that might happen sooner than we think, because there's one more possibility we haven't fully considered, one that's both more hopeful and more strange than anything we've discussed so far. What if they're already here? Not in the UFO conspiracy sense, but in a way that's simultaneously more subtle and more profound than anything we've imagined. The zoo hypothesis suggests that advanced civilizations know we exist. They're watching. They're deliberately staying hidden. And there might be good reasons for their silence. Think about how we study uncontacted tribes in the Amazon. We observe from a distance. We don't land helicopters in their villages. We don't hand them smartphones and explain quantum mechanics. We let them develop naturally, on their own timeline, without contaminating their culture with ours. Now scale that up, way up. If a civilization is even 1,000 years ahead of us technologically, the gulf between us and them would be vastly greater than the gap between us and those uncontacted tribes. They might view interference as not just unethical, but potentially catastrophic for our development. This isn't a new idea. Russian rocket scientist Konstantin Tsiolkovsky proposed something similar in the 1930s, decades before Fermi asked his famous question. He suggested we might be quarantined, protected while we figure things out on our own. But here's where it gets interesting. For the zoo hypothesis to work, it requires coordination, not just one civilization choosing to leave us alone, but all of them. Every single spacefaring species in the galaxy would need to agree. Earth is off limits. That sounds impossible until you consider timing. Monte Carlo simulations suggest that the first civilization to emerge in the Milky Way could have a head start measured in hundreds of millions of years, not thousands, not millions, hundreds of millions. A civilization with that kind of temporal advantage wouldn't just be more advanced. They'd be functionally omnipotent from our perspective. They could have established the rules of galactic contact billions of years ago, and every subsequent civilization that arose would inherit those protocols. It's like arriving at a party where everyone already knows the rules. You learn them from the people who got there first. And if the first civilization that emerged was non-interventionist, that philosophy could have propagated throughout the galaxy. Even if that original civilization is long gone, their legacy persists. Maybe through tradition, maybe through artificial intelligence designed to enforce the policy indefinitely, maybe through something we can't even conceptualize yet. But this raises an uncomfortable question. If they're watching, when do they reveal themselves? Some versions of the hypothesis suggest contact happens when a species reaches certain technological or ethical milestones. Others propose that contact is withheld until we force the issue by visiting their worlds, like a cosmic coming-of-age ritual. Star Trek fans will recognize this as basically the prime directive. And while that's fiction, the logic isn't absurd. Advanced civilizations might genuinely believe that premature contact damages younger civilizations in ways we can't predict. Or maybe it's simpler than that. Maybe we're just not interesting enough yet. Consider what we've accomplished so far. We've barely left our planet. We've sent a few probes beyond our solar system, but they won't reach another star for tens of thousands of years. Our radio signals have traveled about 100 light years, a tiny bubble in a galaxy that's 100,000 light years across. From an outside perspective, we might look like a civilization in its infancy, potentially interesting in the future, but not worth disrupting right now. There's also a darker interpretation called the the laboratory hypothesis. Same basic setup. They're watching, but instead of passive observation, they're actively experimenting on us. Earth as a giant petri dish. That sounds paranoid and narcissistic, but it's not entirely implausible if you assume altruistic motives. Maybe they're trying to help us overcome the great filter by subtly influencing our development, steering us away from extinction without revealing themselves. Or maybe not. Maybe we're just one of thousands of planets they're monitoring, and we're not special at all. The zoo hypothesis faces serious criticism, though. The biggest problem is that it requires a conspiracy of galactic proportions. Every single civilization would need to maintain perfect secrecy for potentially millions of years. No defectors, no rogue explorers, no accidents. When has that ever worked? We can barely keep government secrets for a few decades. The idea that hundreds or thousands of civilizations could coordinate perfect silence seems absurd. Unless the coordination isn't voluntary. What if the first civilization didn't just establish protocols? What if they established enforcement? An artificial intelligence designed to ensure compliance across the entire galaxy. A cosmic referee that prevents contact until certain conditions are met. That sounds like science fiction. But so did GPS, smartphones, and AI-generated art until recently. If we can already imagine such systems, a civilization millions of years ahead of us could certainly build them. Recent research published in Nature Astronomy has narrowed down the possibilities dramatically. After reviewing dozens of proposed solutions, the researchers concluded there are really only two viable explanations. Either intelligent life is extraordinarily rare, or the zoo hypothesis is correct. Not both. One or the other. That's a stark framing. It suggests that all the intermediate solutions, maybe they're too far away. Maybe they haven't detected us yet. Maybe they're communicating in ways we can't detect. Don't actually hold up under scrutiny. The universe is too old and too large for those explanations to work. If life were common, someone should have colonized the galaxy by now. The fact that they haven't suggests either nobody's out there or everyone's deliberately hiding. But here's the hopeful part. Unlike some solutions to the Fermi Paradox, the zoo hypothesis is testable. Eventually, if we're living in a simulation designed to hide evidence of aliens, we might never discover the truth. But if we're simply being avoided, our advancing technology will eventually catch up. We'll develop telescopes powerful enough to image exoplanets directly. We'll detect biosignatures in their atmospheres. We'll see megastructures if they exist. Even if they're hiding their spacecraft, they can't hide their homeworlds. Not forever. Not from a civilization that's actively looking. So if the zoo hypothesis is correct, contact becomes inevitable. Not because they choose to reveal themselves, but because we become sophisticated enough to find them despite their efforts to remain hidden. That's assuming we survive long enough to reach that level. And that's the real catch with the zoo hypothesis. It doesn't solve the great filter problem, it just postpones the question. If aliens are deliberately avoiding contact until we reach certain milestones, what are those milestones? Technological, ethical, social. And what happens if we don't reach them? Do they just keep watching as we destroy ourselves? Or is there a point where they intervene? We don't know. And that uncertainty might be the most unsettling part of this entire scenario. Because if the zoo hypothesis is correct, we're being evaluated, tested, judged by standards we don't understand, by beings we can't see, with consequences we can't predict. It's like taking an exam where nobody told you the subject, gave you the questions, or explained the grading criteria. You just have to figure it out and hope you pass. Some find that idea comforting. We're not alone. We're being watched over, protected perhaps from dangers we don't yet understand. Others find it infantilizing. We're cosmic children in a playpen, kept isolated until the adults decide we're ready for the real universe. Both reactions are valid, and both might be wrong, because there's another possibility that combines elements of several solutions we've discussed. What if the galaxy isn't silent because of a conspiracy or a filter, but because of something more fundamental about how civilizations develop? What if the very nature of advanced intelligence leads to outcomes we haven't considered? Recent research from the Carnegie Institution and Caltech proposes exactly this. They suggest civilizations face a fundamental crisis related to growth and resource consumption that has nothing to do with war or catastrophe. The problem is mathematical: superlinear scaling. Cities demonstrate this principle clearly. As cities grow, their productivity and energy consumption don't increase linearly, they accelerate. A city twice as large doesn't just use twice as much energy, it uses more than twice as much. The relationship is exponential. Apply that to an entire planetary civilization, and you get a troubling pattern. Growth leads to crisis, which requires innovation to solve, which enables more growth, which leads to bigger crises that require even more frequent innovations. It's a treadmill that speeds up the longer you run on it. Eventually, according to this model, civilizations face a choice. They either collapse from burnout, unable to innovate fast enough to stay ahead of their own growth, or they achieve what the researchers call a homeostatic awakening. They consciously choose to stop growing, not because they've gone extinct, not because they've been prevented from expanding, but because they've reached a point where they prioritize long-term stability and well-being over endless growth and expansion. These civilizations still exist. They're just not colonizing the galaxy because they've decided not to. They've turned inward, focusing on sustainability rather than conquest. This would explain the Fermi Paradox perfectly. The galaxy is full of advanced civilizations, but none of them are expanding because expansion is precisely what they've evolved beyond. They're not hiding from us. They're not watching us. They're simply living their lives in ways that don't involve shouting into the cosmos or building Dyson spheres. From our perspective, they'd be invisible. Not because they're trying to be, but because we're looking for the wrong things. We're searching for civilizations that behave like us, expansionist, aggressive, resource-hungry. But maybe that's just a phase, an adolescent stage that mature civilizations grow out of. If that's true, it has profound implications for our own future. It suggests that maybe we should be looking at our own trajectory differently, not as a race to colonize Mars or build megastructures, but as a transition period where we decide what kind of civilization we want to become. Are we going to keep accelerating, keep consuming, keep growing until we hit a wall? Or can we make the conscious choice to step off the treadmill before it throws us off? That's the homeostatic awakening. And if it's real, if this is the natural evolution of technological civilizations, then the Fermi Paradox isn't really a paradox at all. The galaxy is full of life. We just can't see it because we're looking for empires when we should be looking for gardens. But there's a darker possibility embedded in this theory. What if civilizations don't all make it to that awakening? What if most of them burn out first? The mathematics are unforgiving. Each crisis requires innovation to solve. Each innovation enables more growth. Each growth cycle creates bigger crises that require faster innovations. The treadmill speeds up exponentially. At some point, the interval between crises becomes shorter than the time needed to develop solutions. That's when civilizations collapse. Not from war or plague or asteroid impact, but from exhaustion, from running out of tricks, from reaching the point where they simply can't adapt fast enough to their own success. And here's what makes this particularly unsettling. We might be watching it happen in real time. Climate change, resource depletion, biodiversity collapse, social instability. These aren't separate problems. They're all manifestations of superlinear scaling. We're growing faster than we can manage the consequences of that growth. The question isn't whether we'll face these crises. We already are. The question is whether we can innovate fast enough to solve them before the next ones arrive, and whether we can keep doing that indefinitely, or if we'll eventually reach our homeostatic awakening and make a different choice. This brings us to another proposed solution that takes a completely different approach, one that suggests the problem isn't with civilizations at all, but with our assumptions about intelligence itself. The cognitive horizon hypothesis asks a disturbing question. What if alien civilizations aren't hiding or extinct or deliberately non-expansionist? What if they're all around us, but we literally cannot perceive them because our minds aren't equipped to recognize intelligence that doesn't look like ours? Think about how much of your understanding of the world is filtered through human cognition. You recognize patterns that matter to human survival. You process information in ways that helped your ancestors navigate an African savanna. Your entire framework for understanding intelligence is based on one example: human intelligence. Now imagine an intelligence that evolved in a completely different environment, maybe in the crushing pressure of a subsurface ocean, maybe in the complex chemical gradients of a gas giant's atmosphere, maybe distributed across a fungal network spanning an entire continent. Would you recognize it as intelligence? Would you even perceive it as a thing that exists? We've spent decades searching for radio signals because that's how we communicate. But what if advanced civilizations communicate through modulated gravitational waves, or quantum entanglement, or some other method we haven't discovered yet? We're listening for their version of hello, while they might be conducting an entire galactic conversation using a medium we don't know exists. This isn't just about technology. It's about the fundamental structure of consciousness itself. Human intelligence is tool-using, language-based, and socially organized. We build things, We name things. We form hierarchies and institutions. But intelligence doesn't have to work that way. An intelligence based on distributed processing might not have a concept of individual or self. An intelligence that experiences time differently might not have linear causality. An intelligence with radically different sensory organs might inhabit a perceptual reality so alien that communication would be literally impossible. Not difficult, impossible. Like trying to explain color to something that has no concept of electromagnetic radiation. The words don't translate because the underlying concepts don't exist. This hypothesis suggests we might be surrounded by alien intelligence and never know it, not because they're hiding, but because the cognitive gap between us is so vast that mutual recognition is impossible. We're like ants trying to understand the internet. The thing we're looking for is all around us, but we lack the conceptual framework to perceive it. If this is true, the Fermi Paradox isn't a paradox. It's a statement about the limits of perception. The universe could be teeming with intelligence, but each form of intelligence inhabits its own cognitive universe, fundamentally isolated from all the others by the structure of consciousness itself. That's simultaneously comforting and terrifying. Comforting because it means we're not alone. Terrifying because it means we're forever alone, unable to bridge the gap between different forms of mind. But there's an even stranger possibility that emerges when you combine several of these solutions. What if the answer to the Fermi paradox is all of the above? What if life is rare but not impossible? What if there are great filters, but different civilizations fall at different stages? What if some civilizations achieve homeostatic awakening while others burn out? What if some are watching us while others are cognitively isolated from us? The universe is old, unimaginably old. Our sun is a third-generation star, formed from the remnants of previous stellar generations. The Milky Way has been capable of supporting Earth-like planets for at least 10 billion years. We've been technological for maybe 200 years. In that vast span of time, countless civilizations could have risen and fallen. Some might have destroyed themselves with nuclear weapons in the 1960s, equivalent of their development. Others might have succumbed to AI or climate change or some other filter. Some might have achieved transcendence or uploaded themselves into digital substrates or found ways to exist we can't imagine. The galaxy could be a graveyard and a garden and a zoo and a busy metropolis all at the same time, just operating on timescales and in ways that make each civilization invisible to the others. We're not seeing evidence of aliens because we're looking for a specific thing. Technological civilizations at roughly our level of development, using technologies we can detect, in the narrow window of time when they're both detectable and still expanding. That's an absurdly specific search criterion. It's like standing in a forest and declaring it empty because you don't see any other humans wearing exactly the same clothes as you. The forest isn't empty. You're just not recognizing the other forms of life because you defined life too narrowly. This realization should change how we think about SETI and the search for extraterrestrial intelligence. Maybe we need to broaden our search parameters. Look for things we don't expect. Be open to evidence that doesn't fit our preconceptions. But it should also change how we think about ourselves. Because regardless of which solution to the Fermi paradox is correct, they all point to the same conclusion. We're in a critical period. Whether we're facing a great filter, approaching a homeostatic awakening, or simply trying to mature enough to join whatever galactic community might exist, the choices we make in the next century will determine not just our fate, but potentially the fate of consciousness itself in our corner of the galaxy. If we're alone, we carry the responsibility of keeping the flame of intelligence alive. If we're not alone, but isolated by cognitive horizons, we represent a unique expression of consciousness that will never exist again if we fail. If we're being watched, we're taking a test whose results matter to beings we can't imagine. No pressure or anything. The strange thing about the Fermi paradox is that it keeps pointing back to us. We started by asking where everyone else is, but we keep arriving at questions about who we are and what we're going to become. Maybe that's the real purpose of the paradox. Not to find aliens, but to find ourselves. To understand our place in the universe by contemplating the absence of evidence for others like us. Every solution we've explored tells us something about human nature. The great filter reveals our fears of self-destruction. The zoo hypothesis reflects our hope that someone wiser is watching over us. The homeostatic awakening shows us a path forward if we're brave enough to take it. The cognitive horizon reminds us that our way of thinking isn't the only way of thinking. So where does this leave us? Floating on a rock in space, asking questions we might never answer, looking for neighbors who might not exist, or might exist in ways we can't perceive, or might be deliberately avoiding us, or might have destroyed themselves millions of years ago. The honest answer is we don't know. We have theories and hypotheses and educated guesses, but we don't know. The universe is still keeping its secrets. What we do know is this: we're here, conscious, asking questions, looking up at the stars and wondering if anyone is looking back. That capacity for wonder, that drive to understand, might be the rarest thing in the universe. Or it might be common. Either way, it's precious. The Fermi paradox teaches us that the universe is under no obligation to make sense to us. It doesn't have to provide easy answers or clear signs. It can be silent for reasons we can't fathom, populated in ways we can't detect, or structured according to principles we haven't discovered. And somehow, that makes the search more meaningful, not less, because we're not just looking for aliens anymore. We're looking for our future. We're trying to understand if there's a path forward that doesn't end in extinction or stagnation. We're asking if intelligence has a destiny beyond its origin planet. These aren't abstract questions. They're practical ones, with immediate implications for how we organize our societies, develop our technologies, and make choices about our collective future. Every decision we make about climate, AI, nuclear weapons, space exploration, and social organization is informed by assumptions about where we fit in the cosmic story. Are we the first? Are we the last? Are we typical or unique? Are we being watched or ignored? Are we about to pass through a filter or approaching an awakening? We don't know. But asking the question changes us. It forces us to think beyond the next election cycle or fiscal quarter. It demands that we consider our legacy not just to our children, but to the universe itself. The search itself matters, not because we'll necessarily find what we're looking for, but because looking changes who we are. Consider what humanity has accomplished just by taking the Fermi Paradox seriously. We've built radio telescopes that can detect whispers from across the galaxy. We've launched probes that carry messages to potential cosmic neighbors. We've developed technologies to analyze the atmospheres of distant planets for biosignatures. We've created mathematical frameworks to think about civilizations we've never met. None of this would exist if we just shrugged and said, "Guess we're alone." The paradox has driven us to become better observers, better thinkers, better stewards of our own planet. Every attempt to solve it has expanded our understanding of biology, chemistry, physics, planetary science, and our own psychology. Take biosignatures. The search for alien life has forced us to think deeply about what life actually is. Not just Earth life, but life as a universal phenomenon. What chemical processes are truly necessary? What environmental conditions are sufficient? Could life use different solvents than water? Could it metabolize in ways we haven't imagined? These aren't idle questions. They're reshaping astrobiology and pushing us to look for signs of life we might have missed because we were too focused on finding Earth 2.0, or consider Techno signatures. The signals we're searching for reveal assumptions about what technology looks like, how it develops, what purposes it serves. Radio waves made sense when we were a radio civilization, but we're already moving beyond that. What comes after? What would a truly advanced civilization use? Some researchers suggest looking for waste heat. Any civilization using significant energy will radiate thermal signatures. Others propose searching for evidence of stellar engineering. Dyson spheres, or swarms that harvest a star's entire output. The James Webb Space Telescope is now capable of detecting atmospheric chemistry on exoplanets, industrial pollutants, CFCs, the kind of chemicals that only come from technological activity. We might find evidence of alien industry before we find evidence of alien intelligence. But here's what makes this particularly interesting. The search forces us to confront what we mean by advanced or intelligent or technological. We assume these terms are objective, but they're deeply colored by human experience and values. An alien species might consider consciousness itself to be a primitive stage. They might have transcended it entirely, existing as pure information or energy patterns we wouldn't recognize as life at all. Or they might never have developed technology in our sense, instead evolving biological capabilities that solve the same problems. What if the Great Filter isn't about survival, but about transcendence? What if civilizations reach a point where physical exploration of the universe becomes unnecessary or unappealing? They might discover something that makes the material universe seem trivial, some form of consciousness expansion or reality manipulation that renders space travel as quaint as we might view a horse and buggy. This connects to another overlooked aspect of the paradox: timescales. We've been transmitting radio signals for barely a century. In cosmic terms, that's not even a blink. We've been seriously listening for alien signals For maybe 60 years, the universe is nearly 14 billion years old. Civilizations could have risen and fallen entirely within gaps shorter than human history. They might exist right now on the other side of the galaxy, and we won't know for 100,000 years, because that's how long their signals take to reach us. Or consider this. What if everyone is listening, but nobody's transmitting? If every civilization reaches the same conclusion that broadcasting your existence might be dangerous, you get a galaxy full of observers and zero broadcasts. The dark forest hypothesis, named after Liu Cixin's novel, suggests exactly this. The logic goes, any civilization that reveals itself risks destruction from a more advanced civilization that views all other life as a potential threat. So everyone stays silent, hiding in the cosmic dark forest, afraid to light a fire that might draw predators. It's a paranoid solution, but not an irrational one. We have no idea what's out there. Broadcasting our location and capabilities might be the cosmic equivalent of a gazelle shouting, "I'm over here and I'm delicious." But this creates its own paradox. If everyone follows this logic, then the first civilization to broadcast has already broken the silence. Why haven't they? Either there is no first civilization, or the dark forest logic is wrong, or the first civilization didn't survive long enough to matter. You see how each solution opens new questions? That's not a bug. That's the feature. The Fermi Paradox isn't a problem to be solved and filed away. It's a framework for thinking about the biggest questions we can ask. Some researchers have suggested that the paradox itself might be based on flawed assumptions. We assume that interstellar colonization is desirable or even possible, but maybe it's neither. The distances between stars are almost incomprehensible. The nearest star system is over 4 light years away. With our current technology, a journey there would take tens of thousands of years. Even at a significant fraction of light speed, still centuries. Maybe the economics never work out. Maybe the energy requirements are too steep. Maybe biological beings simply can't survive the journey, and artificial beings don't have the motivation to spread. Or maybe they do spread, but slowly, so slowly that they haven't reached us yet. The galaxy is 100,000 light years across. Even traveling at 10% of light speed, colonizing the entire galaxy would take millions of years. That sounds like forever, but it's only a tiny fraction of the galaxy's age. If civilizations are rare and spread slowly, the probability that one has reached Earth specifically is actually quite low. We might be in a colonization wave that just hasn't arrived yet. This is called the Aurora hypothesis, after a science fiction novel that explored these themes. It suggests that interstellar travel is so difficult and colonization so slow that most of the galaxy remains unexplored, not because civilizations don't exist, but because space is really, really big and really, really hard to cross. But there's a counter-argument: self-replicating probes. You don't need to send biological beings. You send machines that can reproduce themselves using materials from asteroids and moons. Each probe creates more probes, and they fan out across the galaxy exponentially. The math on this is striking. Even with conservative assumptions about probe speed and replication time, the entire galaxy could be explored in just a few million years. Where are these probes? Maybe they're here. Maybe they've been here. Maybe they are here right now, and we just don't recognize them. If a probe wanted to remain hidden, it could. Park it in the Kuiper belt or the Oort cloud. Make it small and cold and quiet. Watch and wait and report back to whoever sent it millions of years ago. This is called the Bracewell probe hypothesis. Named after engineer Ronald Bracewell, it suggests that alien civilizations might use automated probes for exploration and first contact, waiting until a civilization develops sufficient technology before revealing themselves. There's something both reassuring and unsettling about this idea. Reassuring because it means we might not be alone. Unsettling because it means we might be under observation without knowing it. Our entire history might be someone's data set. But let's zoom out again. All of these solutions share something in common. They try to explain the paradox while maintaining our basic assumptions about physics, biology, and the nature of intelligence. What if those assumptions are wrong? Not slightly wrong, but fundamentally wrong. What if the universe operates according to principles we haven't discovered yet? Consider quantum mechanics. Before we understood it, classical physics seemed complete. A few weird observations didn't fit, but surely they'd be explained eventually. Then quantum mechanics revealed that reality at small scales is nothing like what we thought. Particles exist in superposition. Observation affects outcomes. Entanglement connects distant objects. What if there's another revolution coming? Something that changes how we think about space, time, consciousness, or information itself. Such a revolution might explain the Fermi Paradox by revealing that our current search methods are looking in entirely the wrong places or the wrong ways. Some physicists speculate about civilizations that have learned to manipulate space-time itself, not just traveling through it, but reshaping it, creating pocket universes or accessing higher dimensions. If that's possible, why would anyone bother with slow, expensive interstellar travel? You'd just step out of normal space-time entirely. The galaxy would be full of civilizations, but they were all in their own engineered reality bubbles. Occasionally, they might peer out at the base level of reality, see primitive species like us struggling with chemical rockets, and think, how quaint. They haven't figured out dimensional engineering yet. We can't prove this wrong. We can't prove it right either. That's the frustration and the fascination. The paradox exists at the boundary of what we can know. But here's what we can do. We can keep improving our ability to observe and understand. Every new telescope, every new detection method, every new theoretical framework gives us more tools to work with. The search for extraterrestrial intelligence has evolved dramatically just in the past decade. We're no longer just listening for radio signals. We're looking for optical pulses, atmospheric biosignatures, stellar engineering, and even quantum communication methods. We're getting better at recognizing that intelligence might not look like us, or think like us, or value what we value. The cognitive horizon is expanding. We're learning to look for the truly alien rather than just the slightly different. And maybe that's the real answer to the Fermi Paradox. Not a single solution, but a process, a continuous expansion of our search space and our conceptual frameworks until we either find something or exhaust the possibilities. The paradox has already given us so much. It's inspired scientific research, philosophical inquiry, and cultural reflection. It's forced us to think about our place in the cosmos and our responsibility to our own survival. Every solution we've explored, from the Great Filter to the zoo hypothesis, to homeostatic awakening to the cognitive horizon, tells us something valuable about ourselves and our universe. Even if we never find aliens, the search has made us more thoughtful, more humble, and more aware of how precious and fragile our existence is. The silence of the cosmos isn't empty. It's full of possibility, mystery, and meaning. It's a canvas on which we project our hopes and fears, our assumptions and blind spots. It's a mirror that reflects back our own nature while hinting at realities beyond our comprehension. Where is everybody? We still don't know, but asking the question has already changed us, and continuing to ask it might change us even more. So what does this mean for us right now, in this exact moment of human history? We're living in a unique window. We have telescopes powerful enough to detect atmospheric biosignatures on distant planets. We have radio telescopes that can listen for signals across vast distances. We're developing AI that might help us recognize patterns we'd never see on our own. But we haven't yet made contact. We haven't found the evidence. We're still asking Fermi's question, just with better tools. This window won't last forever. Either we'll find something, or our capabilities will plateau, or we'll face our own great filter moment. The next few decades matter enormously, not just for answering the paradox, but for determining whether humanity survives long enough to keep asking. Consider what we're actually doing when we search for extraterrestrial intelligence. We're not just looking for aliens. We're testing our assumptions about intelligence, technology, and civilization itself. Every null result forces us to refine our theories. Every new search method expands what we're capable of detecting. The James Webb Space Telescope is currently analyzing the atmospheres of exoplanets, looking for chemical signatures that shouldn't exist without life. Not radio signals, not megastructures, just oxygen and methane in combinations that geological processes can't explain. If we find those signatures, the paradox shifts immediately. We'll know life exists elsewhere, even if it's not technological. But here's what's fascinating about that scenario. It wouldn't solve the paradox. It would make it worse. Because if simple life is common, if we find biosignatures on multiple worlds, then the question becomes even more urgent. Why don't any of those biospheres produce civilizations we can detect? The Great Filter would loom larger, not smaller, unless biosignatures everywhere mean something different. What if the universe is full of biospheres that never developed technology? Worlds covered in microbial mats, fungal networks, photosynthetic organisms that persist for billions of years without ever building anything we'd recognize as civilization. That would be its own kind of answer. Intelligence might be the rare thing, not life itself. There's a thought experiment worth considering. Imagine aliens visited Earth at different points in history. 4 billion years ago, they'd find a toxic, lifeless rock. 3 billion years ago, stromatolites and nothing else. 2 billion years ago, the same. 1 billion years ago, still just single cells. 500 million years ago, Finally, some complex life, but nothing remotely intelligent. 65 million years ago, dinosaurs, impressive but not technological. 10,000 years ago, humans, but with no radio, no satellites, nothing detectable from space. The window where we've been detectable is incredibly narrow. Less than a century, a cosmic eye blink. If aliens visited at any other time in Earth's history, they'd conclude this planet was either lifeless or stuck at a pre-technological stage. They might never come back to check. Multiply that timing problem across the galaxy. Civilizations might rise and fall on different schedules, never overlapping in a way that allows contact. We could be surrounded by ruins and don't even know it, or by civilizations that existed a million years ago and moved on to something we can't perceive. This temporal mismatch idea has a name, the timing hypothesis. It suggests the universe could be full of civilizations, just not at the same time. We're all ships passing in the night, separated by vast gulfs of time as much as space. Some have already burned out, others haven't emerged yet. We might be the only ones currently at this technological stage, looking out at a galaxy full of echoes and potential. But that assumes civilizations only last briefly. What if some make it through? What if there are survivors of the Great Filter, beings that solved the sustainability problem, that achieved homeostatic awakening, that learned to live without destroying themselves? Those civilizations would have a choice. Do they expand? Do they hide? Do they watch? The zoo hypothesis suggests they watch. But there's a variation that's even stranger. What if they don't watch because they don't care? Not out of malice, but because they've transcended the concerns that drive expansion. They've solved the problems they needed to solve. They have everything they want. Why would they bother exploring or colonizing when they've created perfect virtual realities, or uploaded themselves into computronium, or discovered some form of existence we can't even imagine? From our perspective, obsessed with growth and expansion and discovering what's out there, this seems impossible. Why wouldn't they want to explore? But that might be revealing our own assumptions, our own drives, our own limitations. A truly mature civilization might have motivations we can't comprehend, which brings us back to the cognitive horizon. Maybe the paradox persists because we're asking the wrong questions entirely. We're looking for radio signals from beings who might communicate through quantum entanglement. We're looking for megastructures built by beings who might have learned to manipulate space-time directly. We're looking for expansion from beings who might have discovered that consciousness itself is more interesting than physical reality. Every solution to the Fermi Paradox makes assumptions. The Great Filter assumes civilizations follow a similar developmental path. The zoo hypothesis assumes aliens think enough like us to have coherent motivations for hiding. The timing hypothesis assumes civilizations have comparable lifespans. Even the cognitive horizon idea assumes there's something to detect if only we knew how to look. What if the answer is simpler? What if we're just first? Someone has to be first. In a universe 13.8 billion years old, with star formation that varied dramatically over time, with planetary systems that needed multiple generations of stellar nucleosynthesis to produce the heavy elements needed for life. maybe we're genuinely the first technological civilization to emerge, not because of a great filter, not because we're special, just because of timing and probability. This is called the firstborn hypothesis. It's unpopular because it seems to violate the Copernican principle, the idea that we're not special or central. But the Copernican principle doesn't mean we can't be first. It just means we shouldn't assume we are without evidence. And the evidence, the great silence, might actually support it. If we are first, the galaxy is ours to shape. The future of intelligence in the Milky Way depends entirely on what we do next. That's an enormous responsibility. It means every decision we make about our own survival, about AI development, about climate change, about nuclear weapons, isn't just about us. It's about whether intelligence continues to exist in this corner of the universe. But being first doesn't solve the paradox completely, because the universe is older than our galaxy. Stars were forming 13 billion years ago. Planets existed before Earth. Life could have started earlier elsewhere. So even if we're first in the Milky Way, what about the other 2 trillion galaxies? Surely some of them have civilizations older than us. The answer might be distance. Galaxies are separated by such vast gulfs that intergalactic travel is orders of magnitude harder than interstellar travel. Even if other galaxies are full of advanced civilizations, we might never detect them. They're simply too far away for their signals to reach us at detectable strength, or for them to reach us physically. This creates a form of cosmic isolation. Each galaxy might be its own separate experiment, its own unique story of how intelligence emerges and evolves. We're not alone in the universe, but we might be effectively alone in our region of it. The neighbors exist, but we'll never meet them. There's something both lonely and liberating about that idea. Lonely because it means we truly are on our own in shaping the future of this galaxy. Liberating because it means there's no ancient empire to encounter, no galactic federation to join, no test we have to pass. We get to decide what happens next. The Fermi Paradox ultimately isn't about aliens. It's about us. It's a mirror that reflects our hopes, fears, assumptions, and blind spots. When we ask, where is everybody? We're really asking, what does it mean to be a technological civilization? And what is our future? Every proposed solution tells us something. The Great Filter warns us about existential risks. The zoo hypothesis suggests advanced ethics might require non-interference. Homeostatic awakening proposes that sustainability requires abandoning growth. The cognitive horizon reminds us that our understanding is limited. The timing hypothesis shows us how vast cosmic time truly is. We don't know which solution is correct. We might never know. But the question itself has value. It's pushed us to build better telescopes, to think more carefully about our own survival, to consider what forms intelligence might take, to recognize both how special and how fragile our existence is. The search continues. New telescopes are being built. New detection methods are being developed. The list of exoplanets grows daily. Our understanding of biology and intelligence deepens. Every year we get slightly better at answering Fermi's question. Even if the answer remains elusive, maybe the real resolution to the paradox is this: the universe is full of possibilities, and we're living in one of them. Whether we're alone first, being watched, or simply looking in the wrong places. We're here. We're conscious. We're asking questions about our place in the cosmos. That might be the rarest thing of all. Not technological civilization, but the capacity to wonder about it. The ability to look up at the stars and ask, where is everybody? That question, and our determination to answer it, might be what defines us as a species. The galaxy remains silent, but we keep listening, keep watching, keep thinking, because somewhere in that silence might be the answer that changes everything, or the silence itself might be the answer, teaching us that we're more alone, more responsible, and more significant than we ever imagined. The silence keeps getting louder. Every new exoplanet we discover, every potentially habitable world we catalogue, every Earth-sized rock orbiting in the Goldilocks zone of a distant star, they all make the absence more striking. We've gone from wondering if planets exist to knowing they're everywhere. Billions of them, tens of billions just in our galaxy. And still nothing. No signals, no visits, no evidence whatsoever that anyone else is out there asking the same questions we are. But maybe that's changing. Not because we've found aliens, but because we've finally started asking better questions. The Fermi Paradox has evolved. It's no longer just, where is everybody? It's become a framework for understanding the possible trajectories of technological civilizations, a lens through which we can examine our own future, a mirror that reflects back not just cosmic emptiness, but human nature itself. Think about what we've learned just from taking the question seriously. We've discovered that the universe is far more complex than we thought, that intelligence might manifest in forms we can't recognize, that civilizations face critical bottlenecks that could explain why the galaxy isn't colonized, that sustainability might be incompatible with expansion, that our search methods have been embarrassingly narrow. Each proposed solution has pushed science forward in unexpected ways. The Great Filter forced us to study existential risks seriously. Climate science, nuclear proliferation, AI safety. These fields exist partly because we started asking what could prevent civilizations from reaching the stars. We looked outward and learned about threats closer to home. The zoo hypothesis made us consider that advanced ethics might look nothing like ours. That wisdom might mean restraint rather than conquest. That maturity could involve choosing not to interfere even when you have the power to do so. It's changed how some scientists think about our own future expansion into space, suggesting that maybe we should think carefully before we start terraforming Mars or mining asteroids. The homeostatic awakening concept has given us a framework for thinking about sustainability that goes beyond environmentalism. It suggests that endless growth isn't just ecologically unsustainable, it might be cosmologically unsustainable. Every civilization might face the same choice. Keep accelerating until you burn out, or consciously step off the treadmill and find a different way to exist. The cognitive horizon idea humbled us. It reminded us that our way of thinking, our categories, our entire epistemological framework might be inadequate for detecting intelligence that evolved under different conditions. We've spent decades listening for radio signals because that's what we use. How many other communication methods have we missed because we don't know they exist? But here's what might be the most important realization to emerge from decades of thinking about the Fermi Paradox. The answer matters less than the search. We're not going to solve this mystery from our armchairs. We need better instruments, more sophisticated detection methods, broader search parameters, a willingness to look for things we don't expect. The James Webb Space Telescope is currently analyzing exoplanet atmospheres. The next generation of radio telescopes will be thousands of times more sensitive than current ones. AI is learning to recognize patterns in data that humans would never spot. In 20 years, we might have surveyed thousands of potentially habitable worlds for biosignatures. In 50 years, we might have sent probes to nearby star systems. In a century, we might have definitively answered whether we're alone in the galaxy. Or we might not. The universe doesn't owe us answers on our preferred timeline. What we do know is that every civilization capable of asking these questions faces critical choices about how to develop technology safely, about how to manage resources sustainably, about whether to prioritize expansion or stability, about what kind of legacy to leave. These aren't hypothetical concerns. We're living through them right now. Climate tipping points approach. AI capabilities accelerate. Nuclear arsenals remain on high alert. The decisions we make in the next few decades will determine not just whether humanity survives, but what kind of civilization we become if we do. The Fermi Paradox suggests we might be at a critical juncture. Either civilizations routinely fail at this stage, which would explain the silence, or they succeed and transform into something we haven't imagined yet. We don't know which path we're on, but we know we're choosing it right now. With every policy decision, every technological development, every choice about what kind of future to build. That's what makes the paradox more than an academic puzzle. It's a warning and an opportunity, a reminder that intelligence is precious and fragile, that consciousness might be rare, that we have responsibilities that extend beyond our own species, or even our own planet. If we're alone, we're the only witnesses to the universe's beauty, the only minds capable of understanding its laws, the only chance for matter to comprehend itself. That's both terrifying and magnificent. If we're not alone, if civilizations exist but remain hidden or undetectable, then our survival and development might determine whether we ever join whatever cosmic community exists. The test isn't about building the right technology. It's about surviving our own adolescence as a species. The research continues. New theories emerge. Better instruments get built. The search space expands. We're looking for radio signals and optical pulses, atmospheric biosignatures and megastructures, quantum communications and anomalies in stellar evolution. We're getting better at recognizing that intelligence might be everywhere or nowhere, obvious or invisible, familiar or incomprehensibly alien. Somewhere in the data we've already collected might be evidence we don't know how to interpret yet. Some pattern in the cosmic microwave background, some anomaly in exoplanet surveys, some signal buried in decades of radio telescope observations that we'll only recognize when we develop the right framework for understanding it. Or maybe the galaxy really is silent. Maybe we're genuinely alone, or first, or separated by time and distance from anyone else who might exist. Maybe the great filter is real, and we're approaching it. Maybe homeostatic awakening is humanity's next evolutionary challenge. We don't know, but not knowing is better than not asking. The Fermi Paradox has given us something valuable regardless of whether we ever solve it. It's given us a framework for thinking about our place in the cosmos, a reason to build better instruments and develop deeper theories, a reminder that we're part of something larger than our daily concerns, a challenge to become the kind of civilization worth finding. 70 years after Fermi asked his question at lunch, we still don't have the answer. But we've learned to ask it better. And maybe that's the first step toward becoming the kind of species that deserves to hear someone answer back. The galaxy remains silent for now, but we're still listening, still watching, still wondering. And somewhere in that wondering, in that refusal to accept easy answers or give up the search, we're becoming something the universe has never seen before. Or at least something we hope the universe has never seen before. Because if it has, if other civilizations asked these same questions and reached the same conclusions and made the same choices, well, the silence suggests things didn't end well for them. We'd better make sure our story has a different ending. The cosmos is still waiting. The paradox remains unsolved. And humanity's answer to Fermi's question is still being written, one choice at a time, by all of us, right now. That's not just a scientific mystery. That's the most important story being told anywhere in the universe. At least, anywhere we can verify